G'day everyone, today's video is about the nth root of a complex number or the nth root of unity, and then we're going to build that idea once we work our way through here into the nth root of complex number. This is kind of simple once you see where it comes from, because this is kind of a version of that. So concentrate on this and understanding where it comes from. This will fall out for you. So let's have a look. If we get something like this, x cubed equals 1. Okay, that's fine. We could throw it in the calculator. We could get a solution. I want to see where it comes from. You'd agree that moving that over, I can get that, and therefore it'll now equal 0. That's okay, or should be. Now that means that if I put in 1, the real number of 1, into there, it equals 0. So x equals 1 is a solution of that equation there. And hopefully you'd go, well, yeah, of course, that seems fine. I get that. Okay, so that would mean that based on our factor theorem, that would mean that if x equals 1 is a solution of it, then x minus 1 is a factor of it. Okay, say that again. If x equals 1 is a solution to that, then x minus 1 must be a factor of that. Kind of makes sense? Well, that means there's got to be something else that fits in here. Well, I've done it for us, but you can do that in many ways. You could do it by algebraic long division, synthetic division, trial and error, whatever you like, and you should come up with this. Let's just test it. Make sure I've got it right. That one there will definitely get me that there. I'm okay with that. That one there will definitely get me that. So I'm getting back the bits that I want. Now the rest of it needs to cancel out. Can you see that that will give me positive x squared, but that will give me negative x squared. So the positive x squared, negative x squared, they'll cancel out. And then my last one is going to be this blue one. That is going to give me positive x, and this one is going to give me negative x. So that means that while this has a lot of things going on, multiply it out, it falls back to just two things, because all the middle bits cancel out. Okay? So you're happy that this is telling me exactly the same as this, yes, and therefore exactly the same as this. So I haven't changed anything. And we know that mathematics is the art of rearranging everything to a new format. We don't solve much these days. We just rearrange it, make it look crazy. So we're here. We're good. Now, because it's equaling 0, that breaks the null factor law in, doesn't it? Because it equals 0, and I have one thing multiplied by another thing, that says I can use the null factor law. And the null factor law says that if I have two things multiplied together and they equal 0, at least one of them must be equal to 0. Now, if I let this one equal to 0, well, that just gets this solution that I already knew. Okay? If I let x minus 1 equal 0, I get this solution. But if I let this part equal 0, I'm going to get another solution. Now it's a quadratic, so I'm going to use the quadratic formula. Follow along with you. Remember A, B, C, but they're all 1, aren't they? So it's going to be 1, that's, oh, minus 1, sorry, that's B, plus and minus, B squared, minus 4 times A times C, over 2 lots of A. Okay? Because all the coefficients are 1, it's pretty easy here. So then we end up with minus 1 plus or minus, what do we got here? Minus 3, don't we? Minus 3. So could I say square root of 3i? Because the I is the square root of minus 1, isn't it? All over 2. So I've got another 2 solutions here, don't I? Because of the plus and minus, I've got 2 solutions that come out of here. Well, let's graph them up. Let's see what let's look at the geometric interpretation of the solutions. Okay? Remember that point's in the syllabus. This one here, x equals 1. That's 1 on the real axis, isn't it? There's no imaginary. I could write this solution as that, couldn't I? Plus 0i, doesn't change it, but I know now it has no imaginary part to it. So it's not going to be up or down, it's actually just going to be right here. And I'll make that as 1. That's the solution there, isn't it? Right here. Okay? Now then these two, let's graph these two up. Can you see how it's negative a half on the real axis? Negative a half on the real axis. So I'm going to put negative a half there. And then let's build in this idea of the conjugate. If we have a complex solution, we have two solutions, don't we? We have to, because if this part here is 0, we just have a real solution. But because we have a non-zero number underneath the square root sign, and in this case negative to give us that complex solution, then we must have two. We can't just have one complex solution from a quadratic, we have to have two, and they are the conjugate of each other, aren't they? Because of this plus and minus linked with the imaginary part, remember that the conjugate just takes a positive imaginary number and moves it to a negative imaginary number, or vice versa. Okay? So this part is pretty key to saying they're going to be conjugates of each other as complex numbers. So root 3 over 2, take the positive of it, wouldn't that be maybe about here? I'm going to put that. Now root 3, 1.732 divided by 2, about 0.866 decimal equivalents approximately. So this is about 0.866. So you can see there's 1 for me. That's a little bit shorter. And this is roughly half of that. So isn't that also a solution? Isn't that negative a half plus root 3i? And then if I do negative a half minus root 3i, don't I get that solution? So now I have all the solutions on a complex plane, on an Argand diagram of this equation. Now if you went back to last year or the year before, you would have said, oh, the only solution to that's 1. That's all you can get. 1. That's the only solution. When we're looking on the complex plane, we find there's another 2 more solutions to x cubed equals 1. Key points. How many solutions do we have?
3.
What was the power we raised x to?
3.
If I had x to the 5 equals 1, how many solutions do you think there'd be?
5.
Who said 3? Don't say 3. There's 5. X to the 5 equals 1, we'll have 5 solutions. X to the 4 equals 1, we'll have 4 solutions. Now here's the thing. Do you notice anything about the location of these, and take into account my accuracy of diagram? Do you notice anything about the location?
Evenly distributed.
Good. Now can you tell me what the angle is between them?
360 divided by 3.
No, use radians. It's much easier.
2 pi over 3.
Good. Now, think about that. Think about it. 2 pi over 3, you're right. Where did the 2 pi come from? A Fulcrum revolution. And where did the 3 come from?
The 3.
The number of solutions.
Yeah.
So this angle in here is going to be 2 pi over 3, isn't it? Right? And hence the angle here I'm going to write as negative 2 pi over 3. But numerically it's 2 pi over 3. And of course between these is going to be 2 pi over 3 as well. Now the reason I say that's important, the fact you see that this is a full revolution divided by 3, is that if I had x to the 7 equals 1, then the angle between them is going to be 2 pi over 7. I don't need to go through that, I don't need to solve all this. And think, x to the 7 equals 1, this is going to be crazy to solve. Right? I don't want to do that. I want the shortcut. So x to the 7 equals 1 is going to have 7 solutions, starting here with 2 pi over 7, the angle between each solution. Okay? See how I'm making that link to make it easier? So now let's write these solutions down, because I could write them like this in a rectangular format, a plus bi, and that's okay if that's what's asked. But what happens if we want it in R-cis format? Well, R is the modulus. The modulus is going to be 1. Now, if you're unsure about these other two, if you took a half, don't worry about the negative, squared it, and took root 3 over 2, squared it, you get to 1 anyway. Okay? Think about it. A half squared is a quarter. Root 3 over 2 squared is 3 over 4. Add them together, you get 1. Square root of 1, still 1. So these also have a modulus of 1, which is right because that's what we started with. Okay? So now I want to write these as r cis theta. Now this one is going to be 1. Call this as x1. Normally they're termed as z1, z2, z3, but x1 is fine. R cis. Now, if I put cis 0, that's that angle, isn't it? And that kind of works, doesn't it? Because 0, the sine of 0 is 0, isn't it? So effectively, this part of the cis drops out because the angle is 0. The cos of 0 is 1. 1 times 1, I'm back to my original or where I need to be. Okay. The second one, wouldn't it be still 1 because the radius or the modulus is 1? Then wouldn't it just be cis 2 pi over 3? And then depending upon the bounds in which they give you, you could either write 1 cis 4 pi over 3 or 1 cis negative 2 pi over 3. That would be the same, wouldn't it? Just depends which way around you're going. This is the answer if they gave you 0 to 2 pi to work within. This is the answer if they gave you negative pi to pi. Okay? They're the same thing, you've just got to answer the question in the right way. That's about the nth root of unity. On the unit circle, radius is going to be 1. The idea of unity, unit being 1. Okay? Now the second point on the syllabus, I'm just going to come over here and read it. Second point says, determine and examine the nth root of a complex number and their location on the complex plane. Well, here we go. Here's a complex number, 1 plus I. That's a complex number, and I could plot that up pretty easy, couldn't I? I could go, well, here's 1 on the real axis. Here's 1 on the imaginary axis. There we go, there's the point right there. Right? Easy. Now, based on your knowledge now here, how many solutions do you think I will find? 4. And how far separated, how far apart are each one of those solutions going to be?
2 pi over 4.
2 pi over 4, simplified for me?
Pi over 2.
Pi on 2, 90 degrees. So they're going to be 90 degree or pi on 2 lots of each other. So the next solution is going to be over here. And the one after that is going to be here. And the one after that is going to be here. So we'll get 4 solutions 90 degrees or pi on 2 apart. Now then I can go a little further and I can say, well hang on, I want to write them in this kind of format, in a cis format. Well, if I just took these two numbers and did a bit of Pythagoras on them, 1 squared plus 1 squared is 2 square root of 2. So isn't the length of this going to be square root of 2? Got to make sense, doesn't it? And logically, if that one's square root of 2, then they've all got to be square root of 2, don't they?
Yeah.
Okay? So once I've got that sorted, then don't I just need to use these again and do a little bit of tan opposite over adjacent? Think about it. Isn't this 1 and 1? Opposite over adjacent will get me that angle in the middle. In this case, pi on 4. Yep, pi on 4 will fit in here. And then I realise because there's 4 solutions, starting at that pi on 4, I'm going to come around pi on 2, next solution. Around pi on 2, next solution. Around pi on 2, next solution. And then I'll get them all. Okay? So my format really, I'm going to squeeze it in here. I'm going to use Z this time. Let me just make a little mark here. There we go. So I'm going to use Z. Z1 is going to be this guy right here. In cis format, wouldn't that be root 2 cis pi on 4? That makes sense? And then wouldn't Z2, the next one, be the same size, but now we're going to add on pi on 2, aren't we?
Yep.
So are we now going to end up at 3 pi on 4?
Yep.
Is it pi on 2?
I know the original one is this one here, isn't it? That's
I mean,
my...
like, this is pi on
No, pi on 4, because that's my red line there. That's my original one. And I got the pi on 4 by doing a bit of tan. here. Now I'm going to add pi on 2, right? Now I'm adding pi on 2, so then I get to cis 3 pi on 4, which will be this one here. This is Z2. Now have a look at Z3 for me. See if you can work that out. It's going to be root 2 again. It's going to be cis. Now I'm adding on pi on 2. That's the same as adding 2 pi on 4. So wouldn't this go to 5 pi on 4? And then the last one, well, I don't even really need to look at the last one because I've already seen the pattern. Aren't I just adding effectively 2 pi to the top line each time? 7 pi on 4 is 1 3/4 pi, isn't it? So it's 1 3/4. Hey, that makes sense. That makes sense that I'm back to there. Now, if I wrote Z5, would I be finding another solution?
No.
I'd be rewriting the first one, wouldn't I?
Yeah.
Which would be 9 pi on 4, which would simplify down to just pi on 4 anyway. Okay? Key learning here. We've got a new idea here around what we can do with a simple equation. We build in our complex numbers and our solution of a quadratic that does not have a real solution. We see what that comes to, we can graph it. That tells us that, oh, way back here I could have seen 3 solutions equally spaced around, starting here, starting there because it equals 1. And the way I can write 1 is 1 cis 0. So that's how I know it starts there. Okay? Once I know where it starts, how many solutions I have, I can figure out the spacing for each one, and I can get the second and third one and write them down. That's the nth root of unity. This is now the nth root of a complex number, because this is now not what we call unity, unity being 1, this is something a bit more, it's a complex number. It has more to it. So the nth root of a complex number is really kind of the same thing, but instead of starting here, we start wherever that thing is, which usually just rotates it a little bit. Okay? So you can see this as a rotated version of this. I know that has 4 solutions and this only 3. But if I did this one cubed, then it would have 3 solutions rotated a little bit. If I did x to the 4, then it would have 4 solutions here. So I could do the same number of solutions and end up with a very similar picture, one being the rotation slightly of the other.
For that one, the 1 plus I, where are we going to substitute the numbers into?
The numbers in here,
Yeah.
you'll
You'll
be given that in a
I
question.
mean like root 2 cis pi on 4 is a solution, right?
That all of these are solutions to that.
Then how are we going to substitute it in? Because like they are all constants. 1 plus I.
Yes, so what we're saying is that if you get given this, there are 4 different ways to graph that. You might only see the 1 plus I initially, but because it's the power of 4, that's where we're getting our 4 different solutions from. So you would be given something like this and asked to probably show what it equals, and you can expand that out and get it to just a real number and a complex number. Then it will say graph the solutions for that complex number, and this is the solutions, or the 4 possible solutions to that. Just like here, bring it back here. This looks like it's only got 1 solution, right? But in fact, we can find 3 different solutions because of this. This x cubed part is kind of, that's that part there, but it doesn't equal unity, right? Because this is the one of equaling unity equaling 1. This will, and if you put it on your calculator, I don't know what it comes up to be, this will equal something. I'll just make it up for now. Let's say it's 24 plus 16i, right? I don't know what it is, right? But if you expand that out, you'll get something. That is, that whole thing is like this here. But because this is unity, it's a bit simpler. You would be given that normally and said, show that it equals this. Therefore, graph the 4 solutions to that on the complex plane.
what I'm trying to say is that, like, that would be just a point, right?
Oh, sorry. Yeah, maybe I should do this. Putting them in kind of makes me. Yeah, I see what you mean. Yes, yes. So really, you mean like that? Yeah. I'll put the arrows in to kind of show you where I'm moving to. But you're right. That point. It's not everywhere along there. But remember when we do our cis, we kind of display it like this so that we can show the angle. But you're right. It's the points are the solution, not the line. Does that make sense? I guess we should end this video because you probably don't want all these questions. Hopefully you skipped it anyway. See you later, guys. Have a good time.